Welcome to this how-to video in the SEMCA software, where we will discuss some details regarding spectral filters. This how-to video is preceded by two other how-to videos. In the first how-to video, we showed you how to import a spectral dataset into SEMCA and create a SEMCA project file, a so-called USP file. In the second preceding how-to video, we looked at the so-called calibration wizard and familiarized ourselves with how to operate this wizard. The wizard is there to help you to develop multiple multivariate calibration models using different filters and allowing you in an easy way to compare different models. In this how-to video, the intention is not to show you how to build an OPLS model linking spectral data to a specific variable. The intention is to look into some details regarding the spectral filters that are available. The discussion around the different filters should be seen as an introduction to spectral filtering and raising some points of awareness, and it does not give an exhaustive account on the topic of spectral pre-processing prior to building a multivariate calibration using OPLS. In front of us we see the NIR data from the Carrageenan dataset that we introduced in the two earlier recordings. And as you may recall from the preceding how-to video, the initial stages in the calibration wizard consists of defining which spectra to use, which observations to use in the calibration model, and which variables to use, which spectral window to use, the entire spectral window or a subset of the entire spectral window. And once such definitions have been done, you come in the wizard to the stage where you will select different filters, calculate models on those filters, and compare the models. So as you can see from this screen, the filters inside the calibration wizard are grouped under four headings. The smoothing filters, they are there to help you to remove high frequency noise or some spikes from spectra, and there are 5 different filters that are supported here that perform smoothing. Another group of filters aim at baseline correction. These filters will reduce the influence of varying or changing baseline. Another group of filters that are available are so-called normalization filters. These filters help to reduce the effect of changes in signal intensities in the spectra. And such changing signal intensities can be caused by, for instance, a change in the instrument, a fluctuation in the instrument, or some sample variations. In the bottom we have the so-called other category involving multiplicative signal correction, MSC, and derivatives. Another perspective from which to view spectral filters is to look at the different effects that can occur in the spectra. In this presentation I will distinguish additive effects, multiplicative effects, and severe nonlinear effects from each other. An additive effect, that is something that produces a baseline displacement or a baseline shift to the spectra. A multiplicative effect is something that modifies the local slope of a spectrum, not in the entire spectrum, but in a local part. And beyond that, you can have severe nonlinear effects, which essentially means wavelength-dependent variabilities in the spectra beyond additive and multiplicative effects. From now on, I will be switching between different datasets that we have in our examples compilation in our training material to illustrate the effect of different types of filters. And so, like a good chef, I have prepared 3 different instances of Simca in order to facilitate a swift transfer between different scenarios. The first scenario that I would like to illustrate is when you have very noisy data, very wiggly data. Here in front of you, you see some fluorescence spectra. They are part of our tutorial exercise called sugar. So as I said in the opening remark, the objective of the filters in the smoothing group is to remove high frequency noise and short-lived, short-term spikes in the spectra. One of the filters supported in this group is the asymmetric least squares smoothing, and this is what I will exemplify. Here, upon clicking on that button, you see the original spectrum in the top part of the graphical view and the filtered spectrum in the lower part for the first observation or the first spectrum. By clicking Ctrl A, you will see the effect of this smoother across all the 106 spectra being part of this tutorial dataset. And I think the 2 spectral plots speak for themselves. You readily see the effect of using a smoother. Okay. Now I'm going to switch to another use case, which is this one that we used in the earlier recordings. So just a little short recap. What we see here are 128 NIR spectra for different carrageenan samples. And as you can see, when we go from the 1100 up to the 2500 mark, there are 2 things that happen. First of all, there is a baseline variation, but also when going from the lower wavelength end towards the higher wavelength end, there is an increased spread among the spectra. Using this dataset, I'm going to illustrate the impact of baseline correction filters and normalization filters. Under the heading of baseline correction, there are different filters doing the baseline correction in various functions. For instance, the row center, that will remove differences between the NIR spectra, but it will not remove the change in the slope, you can say. Spectra are aligned, but the increasing signal value, signal intensity, going from the left to the right in the spectrum, from the low wavelength end to the high wavelength end, still is there. Conversely, or as opposed to this, the asymmetric least squares correction will also remove this non-linear change. It will better align each spectrum with the reference line or the reference value being 0. So after invoking this baseline correction, the spectra are also aligned, and you can see that the baseline is now quote-unquote horizontal. So these were 2 examples of different baseline correction filters and their impact on the original spectra. Now, continuing using this NIR dataset, I would like to shed some light on some very popular and very commonly used spectral filters. The first one is SNV, Standard Normal Variate, which is part of the normalization group. You can see here that what SNV does is that it will align the spectra very well. A very interesting aspect is that the Standard Normal Variate filter can be regarded as a row-wise scaling and centering in a data set. So in that sense, it complements in a very nice way the common pre-processing used in SIMCA of column-wise centering and scaling. An alternative to SNV that is also very popular is the MSC, the multiplicative signal correction filter. And to my experience, the results that you obtain with MSC and SNV are often almost indistinguishable. They are at least very, very similar. Here we see the effect of applying MSC to the original spectra. And again, you can see a very nice alignment of the original spectra, and the effect of this rising baseline is still there. Another family of spectra that you can apply are derivatives, and they are very good at removing these additive baseline differences. So now when zooming in on the derivatives, you can say that derivatives are just a series of consecutive subtractions, and they are done to amplify changes in the spectra and try to attenuate random noise amplification. Derivatives are often combined with a smoothing algorithm, and inside the SIMCA software, when you apply derivatives, they are connected to the Savitsky-Golay smoothing approach. As you can see in the video, we are supporting 4 types of derivatives, and the details about the natures of these derivatives you can read about in this tool tip. When you open up the derivative window, first of all what you can do is to select the derivative order. Then comes another setting, which is the polynomial order of this Savitsky-Golay smoothing function that I talked about. Savitsky-Golay filter or smoothing window can be thought of as a window gliding along the spectra from left to right or from low to high wavelength. And what we have to set here is the width of that moving window. Just by looking at the first spectrum in this Karajinan dataset, it's very clear that one of the effects of the first derivative or any other derivative, if you choose to look at such plots, is that this change in the baseline, meaning changes in signal amplitudes, is compensated for. And by using the Control A here, you can see how also these additive effects, these changing baselines, are compensated for. So now you have seen how some very commonly used filters, SNV, MSC, and derivatives, here represented by the first derivatives, often work very well with spectra where smooth things take place, such as NIR spectra. I am now going to switch to another instance of the SIMCA software where we have slightly more challenging features going on or taking place in the spectral data. And this is the still the Karajinan dataset. Here in front of us we see the 128 Raman spectra, and as you can see, these spectra exhibit much more pronounced variation compared with the NIR spectra. We have changes in the baseline, additive effects. We have changes in the spectra, definitely arising from multiplicative scatter effects, but maybe also more pronounced non-linear effects. We will use this dataset to show you how you can apply more than one filter. In SIMCA, applying more than one filter in a sequence is known as chained filters. So just to emphasize, the objective of this last part of this how-to video is to show you how you can combine filters in a sequence. The objective is not to fully exhaust all possible combinations in order to optimize the calibration model with regard to the lambda y variable. So I will start by applying the derivative filter to these spectra. You can see how the first derivative in this case removes this increasing signal amplitude when going from left to right in the spectra, or from a high wave number towards a low wave number. Just by applying the first derivative means that the spectra are much better aligned. So we click OK now to preserve this filter. And then in this sequence of chained filters, we will apply the SNV filter. Here you see in the top part the input spectra. This is the output after applying the first derivative spectrum. And in the bottom part you see the effect after applying the SNV filter to the first derivative spectra. As you can see, not much happened throughout the spectral window. One of the noteworthy facts is that in the right-hand part of the spectra there is some considerable variation which the first derivative spectral filter failed to remove, and this rather large variation in signal amplitudes also exists after having applied the SNV filter. Another thing I want to draw your attention to is this peak here around 3000 in the wave number scale. In this region the spectra are very well aligned after first taking the first derivative and then applying the SNV. Just remember this for the next case. As opposed to this, I will now first apply the SNV to these Raman spectra, and you can see the effect of applying the SNV. It aligns the spectra very well, particularly in the right-hand part of the spectrum, the low end of the wave number. The spectra are now much better aligned in this part of the spectral window when compared to applying initially the derivative spectrum. But as opposed to this, in this peak here that I was talking about, we have actually more pronounced variation after applying the SNV compared to applying the derivatives as the first filter. Now, after using the SNV as a filter, we go on and use the derivatives as a filter. And you can see how the derivatives now mitigates some of these amplified variations around the wave number 3000. The peak formation here around the wave number 3000 after applying SNV to the raw Raman data is attenuated using the SNV as a complement to the SNV. And now, in order to round off this how-to video, I have discussed a number of different filters that are available inside the calibration wizard. I have showed you the influence of different types of filters, not all filters, but representatives of each category. And in this last part of this how-to video, I have showed you that you do not necessarily have to use each filter in isolation. On the contrary, you can combine filters. You can combine 2 or 3 or more filters. We have just looked into the possibility of chaining 2 filters, but you can chain more filters. Chaining here means combining several filters in a sequence. But the take-home message from the last part of this demo is that the order in which filters are chained or combined can have a big influence. In this last part, it is definitely so that using the SNV filter prior to any of the derivative filters gives a much better alignment of the 128 Raman spectra, as opposed to the situation when starting with the first derivative or second derivative or any of the derivative filters prior to S and V, or maybe even MSC. Those results are not shown, but in this case, SNV slash MSC prior to the derivative filter family is to be favored. With that said, I say thank you, and I hope you find this recording useful.